Last episode, trees and SVMs made decisions with clever single boundaries. Now we ask, what if we stack many simple transformations on top of each other? Does the network become more than the sum of its layers? Think of a factory line. Raw material comes in, station 1 reshapes it, station 2 reshapes that, and so on. Each station simple, but the line as a whole produces something none of them could alone. A neural network is exactly this. Each layer takes the previous layer's output and transforms it a little. Each station does two things. First, a linear step, multiply the incoming numbers by a matrix of weights and add a bias that mixes and rescales the features. But if every station were only linear, you could collapse the whole line into one matrix and nothing was gained. So after the linear step comes a bend, a non-linearity like ReLU, which simply zeroes out anything negative. That bend is what makes depth worth having. In symbols, each layer computes h equals the nonlinearity of w times x plus b. Compose those, layer 2 of layer 1 of the input, and you get a network. Convolution is a special thrifty version. Instead of a full matrix, you slide one small kernel across the input, multiplying and summing as you go. The output length follows a clean rule: input size minus kernel size plus 1. This is the math of deep learning. The linear then non-linear sandwich is every MLP, every transformer block. Convolution's weight sharing is why CNNs need so few parameters to scan a whole image. One edge detector reused at every position. Stack convolutions and each neuron's receptive field grows, seeing wider context. Pooling downsamples so deeper layers reason about bigger structures. Here's the whole thing in one file. We'll run a tiny 2-layer network forward by hand, then convolve a one-dimensional signal with an edge detecting kernel. We seed and define ReLU, the nonlinearity that clips negatives to 0. We set up a 2-feature input, a first weight matrix and bias, and a second layer that collapses to a single output. We compute the first layer's linear part, apply ReLU, then the second linear layer. That's the full forward pass to one number. We make a one-dimensional signal with a couple of edges and slide a length 2 kernel, -1 then +1 across it. The convolution lights up exactly at the edges, and its length equals input minus kernel plus 1. The convolution arithmetic confirmed. So a network is composition and convolution is shared weight scanning. Next episode, we look at what those vectors flowing through actually mean, embeddings, and the geometry of meaning.